So yeah, equations in quadratic form, it becomes a change in form, and then at the end we have to change it back. And again, maybe that's sounding worse than it is. Yeah, the reason why we can't just leave it the way it is because we need it to be in a quadratic format, right? This is the general polynomial format that we're used to, that trinomial, where the degree of the polynomial is 2, and then it kind of, the degree decreases, right? This is degree 2, this would be 1, and then 0. But what you're going to notice is they're still going to give us a trinomial, but usually the middle term is you could, when we compare the x's or whatever the variable is, they won't always use x. But if they use x, you'll see that the exponent for the middle term is either half of the exponent for the first term. To put this a different way though, like what I'm showing here, usually we compare the first term here with the second term. So I would say, I always look at it and I see, oh, this exponent right here is double whatever the second one is, okay? And what that does is that allows us to change the format, and that's why we say we're going to substitute. This is not necessarily substitution like systems of equations, but it is similar. It's just now we're substituting a base with a specific exponent. So what we do is we say, look at this middle term right here. Instead of showing it as x to the power of p, we say we're going to let this happen. Really, I like to say that we're going to force this to happen because I don't want to see this x to the power of p, whatever it is. I don't want to see that garbage. So I just say, look, I'm just going to change it into a u, because an individual letter like this one is a lot easier to deal with than x to the power of, let's say, 5. Okay. And when I do that, now instead of showing as x to the power of p in the form, I have, because it was b times x to the power of p, since I've replaced that with u, then I have b times u. And then you can see this really just changes back into its regular quadratic form. Now, after that, then we solve that quadratic and replace the u with x to the power of p. So once we get because we're going to solve this quadratic for u, and I don't really understand why they used u, but they did. Then we replace it back with this and then solve for 0. Okay. Check your answers in the original equation. Always do that. It's always, I can't guarantee that all of the answers that you get will be actual solutions. So you do need to check. But again, the calculator should help us to do that. So do not forget to replace the u at the end. I put that part at the end specifically for me, because I tend to forget to put it back, to replace it back, right? Because u does represent some kind of expression. Sometimes it's just x to the power of 2, x to the power of 5, but sometimes it's 3x plus 4 to the power of 8, that with parentheses. And then if you don't replace that back, then you've solved essentially for the wrong thing. And so you got to replace that back. Right now, while we're getting used to this, generally speaking, these are factorable. Okay. Could you use the quadratic formula to solve it? You could. But if I remember right, some of these just kind of lend themselves towards factoring. So I think that's what I'm going to stick with today. All right, so here we go. This one lends itself to substitution. We'll call it u substitution, because mathematically, us math nerds like to use u, because that's what we were trained to do, I guess. All right. So on this one, this one's not asking us to solve. It's just saying, can you tell what you're going to substitute as u? Yeah. Well, yeah. So here's the thing: is that if I were to take the u and what am I replacing with u? I feel like there's a good x joke that goes with this, but I'll skip it. So here's what I'm going to do. I'm going to take that 5x minus 3. Now again, it's not just the base. Remember, I see these exponents here, right? And sure, the 5x minus 3, I see it repeating. Sometimes it's just an x, but now it's 5x minus 3, and that's fine. But I see that this exponent, this leading exponent right here, is double this middle one, right? We always have this constant, so I'm not ever expecting to see any x or exponents with this term. But I do see that this exponent is double this one. Okay, so that tells me that U substitution will work, but it's usually always, it should be, this middle, again, it's not just the base, sometimes it's just x, but also the exponent. So it's actually 5x minus 3 in parentheses to the power of negative 3. Now here's what happens when I do that. So if I were to look back at the original equation, it's not asking us to do this, I'm just showing you because we're going to. Okay, so I'd have 20, and then I'm just looking at the coefficients right now. Plus 6 equals 0. So here's what happens. Well, I just took this 5x minus 3 to the power of, all that to the power of 3. And I said, instead of it being that, I'm going to make it a u. All right, now here's the other thing that happens is we got this 5x minus 3 to the power of negative 6, but that's not 5x minus 3 all to the power of negative 3. Well, what happened was essentially we took this and squared it. So I'm just really multiplying that exponent. And so then u squared equals, it's the same thing, right? It's the 5x minus 3, but now it's to the power of 3 times 2 would be negative 6. So that's why we were able to replace this with u squared. And now it is a quadratic, so you could technically, if you wanted to, solve this with either the quadratic formula, maybe factoring works. I think I tried the factoring, but just to see what would happen. I don't remember what happened, but I don't think it worked. In any case, we didn't really need to go that far. The only thing we needed, let's come back here and just show the substitution that we needed was this part right here. Okay, so again, it's not just that you're taking 5x minus 3 and replacing that with u, you're taking the 5x minus 3 base and the exponent from that middle term and then replacing it with u. Now, even if we were to solve this, which we're not. No, it didn't ask us to solve. We're gonna solve the next ones. But if it did, if we were to solve these, then we would have to make sure once we solved for u, that we would have to replace that u back with this garbage right here. And then we would solve that garbage. This one we will solve. Okay, so let's go through this one together. Now the first thing I do want here is a u substitution because I really don't want to, I especially do not want to have to worry about taking this 2k plus 1 and squaring that garbage. I mean, you could say, well, I want to just distribute negative 14 here, and that's fine, you could. And technically you could if you wanted to square this and then distribute the 8, that's fine as well. Let's see how it works with u substitution. So on this one, I'm going to say, instead of this, I'm looking at the middle term, I guess. Instead of this being a 2k plus 1, and I'm going to put it in parentheses just because it is, but not just here, but here as well. So I'm going to say that 2k plus 1 in parentheses, that is my u. Now, I guess I should have shown this before, but these ones are setting up nicely. The thing that you should notice before you do this is that this exponent here is double this one. Some students say, well, there isn't one there. There is, you just can't see it. It's a phantom one. Okay, so it was there the whole time, just hiding in the shadows, watching, which is kind of freaky. But now that I know what u is, I can also say, well, look, if I were to square that u, then I would square the 2k plus 1, and so 2k plus 1 in parentheses squared would be u squared. That allows me to replace this 2k plus 1 squared as just a u squared. So this is my new equation then. So I've got my coefficients, and this equals 0, and it would be 8 times u squared, and then 14 just times a u. So this now, this trinomial, this polynomial, this quadratic is now, in my opinion, much easier to solve. So let's go ahead and see if we can solve this. So I would look at factoring right here. Again, you're welcome to use the quadratic formula to solve it, but I'm looking at my 8 and 3 there. I'd have to multiply those before I start factoring, and it looks like I got to factor by grouping because my leading coefficient is 8. So 8 times 3 is 24. I need 2 factors of 24 that add up to negative 14. 12 and 2, I believe. I apologize, not just 12 and 2, but negative 12 and negative 2. So this takes us back into one of the more enjoyable times in this class where we were factoring by grouping. So I'm going to take this negative 14u, and instead of it being negative 14u, I mean, it still has the same value, but I'm going to show it differently as negative 12u and also a negative 2u. Now I still have the rest of this equation, right? So I got my 8u squared, and I still got my plus 3 equals 0. And now, of course, factoring by grouping. So right here, I'm going to look at this group first, and from those, I would factor out, looks like a 4u. Okay, so what am I left with in here? Looks like I would be left with the 8 divided by 4 would be 2. I took out a u from the u squared, so it's 2u. And then negative 12 divided by 4 would be negative 3, and then we yanked out that u. Okay, so let's look at the next part here. Let's factor from the negative 2u minus plus 3. I don't want the negative 2 leading coefficient there, so I definitely need to factor out a negative, and it looks like it's going to have to be a negative 1. So if we do that, what's left over? Well, negative 2u divided by negative 1 would be positive 2u. And remember, back from factoring by grouping, it should match this one if it works anyways. 3 divided by negative 1 would be negative 3, so that does force it to match. This still equals 0. And now I can write this as two separate factors. So I would yank out from those two terms a 2u minus 3, but then I would be left with the other factors from both terms, which would have been 4u and negative 1. And yeah, this still equals 0. And I'm going to need more space. So from here, it all equals 0. So we just need to get those factors to equal 0. So let's do that. Let's take that, if I can get that 2u minus 3 to be 0 by itself, that would be enough to make that equal 0. And so solving this one, I would add 3 to both sides. That zeroes that out. Now I got 2u equals 3, and then finally dividing both sides by 2. So u equals 3 halves for this one. Let's solve the next one though. So if that 4u minus 1, if I could get that to equal 0, that would make the equation true. So solving this one, I'd have to add 1 to both sides. That zeroes that out. I got 4u then equals 1, and then divide both sides by 4 makes my u equal to 1/4. All right, now that was most enjoyable, but we are not finished. Like I said, I tend to just solve that, and it's like, look, we factored and we did some substitution, and we feel really good about that. Or maybe we don't. Maybe we hate it. Welcome to math. In any case, what I do understand is that u is not just u. We were solving for u, but it's not just u. It's u equals, remember back up here, u equals 2k plus 1. So I needed to take that u and replace it with 2k plus 1. So instead of a u, it's now 2k plus 1. And this would equal the 3 halves. But also this other u over here, this would be 2k plus 1. And that equals 1/4. A little bit more space there. So let's solve these now. All right, so I'd have to subtract 1 there, so that'd be 0 that out. So I got 2k, 3 halves minus 2 halves, there'd be 1/2. And then divide both sides by 2. Tells us that k here is 1/4. Okay, that's pretty good. How about this one right here? So let's subtract 1 from both sides. So that zeroes that out. I got 2k equals 1/4 minus 4/4 would be negative 3/4. And then now I would divide both sides by the 2. And then k equals negative 3/4 divided by 2 would be negative 3/8. I suppose you could use the decimals on those, but I think that's it. Well, k was the original variable in the original equation, which means that it appears that we have solved the problem. Now, we only got 2 answers. Remember, the exponent here, and if you had actually distributed and multiplied and then solved from there, you would have seen that you would have gotten some k squared. Again, the exponent would have been 2. This is a degree 2 polynomial, so we would have expected 2 answers. Now you can check. You can replace k with 1/4 and -3/8, but I've done that already.
Excellent.
And so, yeah, so, but always make sure that you actually do check these in your calculators, because it's good to practice that, okay? Just, there we go. So, yeah, the difference here is that instead of, in the past, we started with something like this. We have to get to this point. We have to force this to look like this. And then at the very end, once we get to this point right here, we have to remember to replace the u back with what it originally was. So on here, I got x to the power 4 minus 61x squared plus 900 equals 0. Now that is not a power of 2 degree. It's not a degree 2 polynomial. It's a degree 4. And a couple things about that. I would expect 4 answers on this problem. I expect there to be 4 answers. Will there be? I don't know. Let's find out. But I also see my x to the power 4 is double this x to the power of 2, so u substitution should work, right? Well, let's do that then. So my u, again, it should just be the middle value, whatever is squared, or whatever that exponent is, right, with its base. Sometimes and so this one's 2 and 4, right? I see the 4 is double the 2. Again, if it was a 3 and a 6, that would work, or even, well, I guess even a 1 and 2, but we've done those. 4 and 8, 5 and 10, and so forth, okay? Now, again, this tells us then that if you were to square both sides of that equation, the u equals x squared, then you would get u squared equals x squared squared would be x to the power 4. So that tells us that my x to the power 4 there, I could replace with just u squared. And then my x squared, again, instead of it being x squared, it's just u. So now I've got u squared minus 61u plus 900 equals 0. Well, this one, my leading coefficient is a 1, and that's pretty good, because if I can just figure out what 2 factors of 900 would add up to -61, then we have this pretty much solved, right? So I am using u still, though. So it's not x anymore, it's u. Let's just figure out what those 2 factors are. Calculator should be useful here. 900, by the way, is a perfect square, if that means anything. So you could say, well, 30 times 30, which I don't really want. Plus, it doesn't add up to -61. So let's look at some other values here. Maybe I should do this on the left. Let's look at 900. Again, 30 and 30 works. 2 and 450 works. 3 and 300, yeah. 300. Let's see.
4 will work. 5.
Yeah, 9. 6. Yeah, so I'm using the calculator for this. If I divide by 5, divided by 5, 180. Of course, none of these work, right? If you were to add these even as negatives, they wouldn't get you to -61. That'd be too high. I'm going to skip the 10, so 10 and 90. Getting a little closer to 30 and 30. What about 900 divided by maybe 20? Let's try that. So I got 20 and 45. That's close. If we were to make those both negatives and add them to be -65, so I guess that's kind of close. 900 divided by 15. Well, I did have 15 and 60. So again, I guess I got further away there. Thank you. 25 and 36. Boom. Yeah, if we were to make these both negative and add those together, you would get the -61. And so our 2 factors of 900 would be -25 and -36. So those just go right into the 2 binomials, right? So u minus 25 and also u minus 36. And if for some reason you did u minus 36 and u minus 25, it's exactly the same thing. But now that I've gotten this far, I just need to solve these 2 equations, right? So want me to make them equations. So this, meaning if I could get u minus 25 to equal 0, it would make this equation true. So most students don't have to show this, but if it helps you, then, which I hope it does, then use it. That zeroes that out. I got u equals 25. And then over here, I would have to make the u minus 36 equal to 0, which we could by adding 36 to both sides there. So in other words, that zeroes out. U could equal 36. Now, from here, we solved for u, and that was great. But yeah, so at the beginning, we had u is x squared. So instead of it being a u, I have to go back and replace it with what it was, and that was x squared for both of these. Okay, so in other words, x squared should be 25, but x squared should be 36 as well. So right here, to solve these, I would square root both of them. Okay, and I would say, well, x, it could be 5. And over here, if I square rooted both sides, x also could be 6. But we're square rooting from an x squared right here, so we don't actually just want the primary root on those. We need their opposites as well. So x could be 5 or negative 5, or x could be 6 or negative 6, right? Because if you said, well, x is 5, 5 to the power of 2 is positive 25, but negative 5 times negative 5 as well is positive 25. Same with negative 6 times negative 6 would be 36. So there, remember what we were talking about at the beginning, it was an x to the power of 4. It's a 4th degree polynomial, so we do expect there to be 4 answers on this one. Last thing we should do is go back and check. And this one, it's not even that hard. When I did this, I used the store x function, so I didn't have to type in x to the power of 4 minus 61x squared plus 900 all the time. But when I did it, I found all 4 of these do work. So 4 solutions, and they are solutions. That's good. So on this one, again, I see that my exponent for my leading term here is double the middle one, right? I'm looking at the exponent. Even though they're fractions, 1/3 doubled is 2/3. So that's pretty good. And that tells me then that I can use u substitution instead of dealing with those fractional exponents. Oh. Well, another thing I noticed now that I take a better look at this is that the middle coefficient is 0. Even though they're showing minus 0 for some reason. That means this term really perhaps isn't so necessary. And that makes me think it could just be solved using exponents. But
4 times 4.
so I'm going to go through the process just so you can see it, even though we know the middle term is 0, and that's good. So here I would make u be p to the power of 1/3. And again, if I had squared both sides, then u squared, p to the power of 1/3 to the power of 2 would be like taking 1/3, multiplying that by the 2. So that's why p to the power of 2/3 is the same as u squared. Okay, so again, instead of using the base p, I'm going to use u instead. So p to the power of 2/3 now is u squared. And then p to the power of 1/3 is u, even though it's minus 0u. And then this would be minus 16. And that equals 0. Now at this point, well, I'm going to assume that you did not notice that 0u in the middle. So I'm going to work with it, okay? It's still factoring it's not even factoring by grouping. I'm just using the rule for factoring because my leading coefficient is still 1. And so I would be looking for 2 factors of negative 16 that add up to 0. If you want to say negative 0, that's fine as well. It doesn't matter. So negative 16, 2 factors that add up to 0 would be, like you said, 4 and negative 4, right? Now again, my variable here is u. So I've got a u plus 4 and also a u minus 4 there. And if we could get those 2 factors, those 2 binomials, to equal 0, that would be nice. So let's do that. So u plus 4, if I could make that equal to 0, that'd be nice. And we know, again, most students don't usually show this, but if you need to, because it helps, do it. So u could be negative 4 from the first one, but if you made u minus 4 equal 0, then solving for this one, you'd add 4 to both sides. And then you'd see u equals positive 4 as well. But now I need to go back and say, well, u actually was replaced with, it was replacing something else, which means that I need to go back and replace both of these u's with what it was originally, and that was p to the power of 1/3, both of them. So in other words, p to the power of 1/3 could equal -4, or p to the power of 1/3 could be +4. In my mind, I usually do this with, like if I do this in my head, I would think, I'm just going to put these two in root form. But the exponent's actually okay right here, because what I can do with those is, to make it just a p, I would take this and cube it, right? So p to the power of 1/3 times 3 would be, 1/3 times 3 would be 1. And I really don't need that one. But if I do it to one side, I got to do the other side, right? So -4 to the power of 3 would be -64. And I can do the same thing over here. By the way, we would have done this to the power of 3 even if we had made it a root, a third root. But again, we get p equals 4 to the power of 3 is just +64. Now again, you can go back up here and replace those p's with 64 and raise them to the power of 2/3 or 1/3, and 1/3, I guess. And you would get an equation, both equations are equal to 0.